across stuff that makes you feel stupid. A lot of security stuff in computers has done that for a long time these days. You know, I had to learn about things like I had mistaken impressions for a long time about the way that things work. Like I didn't know about cross-origin policy. If you I thought that there may be some very powerful, structural advantages to hacking. Like, for instance, on the internet, if you had your own web domain and you could get people to it, and you could, write JavaScript, for instance, to, you know, gather everybody's cookies. And I guess that this is how it might have worked in the early days of the web and everything. And on early browsers and everything, because the old days when it came to hacking and everything, it was the kind of situation where the web wasn't really designed with any sort of security in mind. And the web still very much so kind of operates that way, in the sense that no matter what you do to try to block certain traffic on the web, for instance, there's 1,000 different ways to route around it. A web admin trying to keep a user out of their website is just it's silly, because it doesn't work in practice. There are 10,000 different ways to circumvent it, and to reroute your traffic in such a way that it's coming from 1,000 different angles. And I mean, this goes back to the spirit of TCP, which is just if one route's blocked, it finds a different way around it. It's redundant, failover, resistant, in that sort of way, and the way that it's all set up. And so, the web, some of the basic fundamental insecurities in the web are still there, but you can't do things like you could in the old days, where, if you ran a website, you could just tell the browser, hey, leak all your fucking cookies to me, because there's shit like cross-origin policies, and a lot of the security upgrades that have happened, like the browser sandboxing and all that other stuff. Like, I didn't know anything about that. Like, I had to be brought up to speed on a lot of it. And I'm looking at this and I can't believe how much they're able to do at the hardware level to secure their systems from any sort of tampering and everything. The mitigation methods and what we would have to do in order to really get at the switch. But I had to, because of a lot of the mistaken impressions that I had to ask some like really fundamental questions to ChatGPT, because I didn't know a whole lot. And a lot of this comes from the fact that, like, I might know and have a lot of experience in the world of software, but not necessarily in the world of or especially troubleshooting software and everything, and things that I've learned about, you know and I've also worked with mod chips before, but I wasn't necessarily the one that installed the mod chips myself on a system and soldered to the board, but it just, when I looked at this, I there was a lot, and unfortunately, if it comes down to this route, the only way to do things is very manually, because ChatGPT doesn't want to give me, the knowledge that it I want it to. It's limiting. It's basically saying, I'm not going to teach you attack vectors for this, and it's like, well, I'm not. I'm just trying to learn from this. I mean, do you think that, like, I'm a single person, okay? Do you think, like, I'm gonna be able to take this information as a hobbyist and, do anything more than a sort of a write up on GitHub about things, and maybe provide die shot analysis, to the the GitHub community about the just Nintendo Switch 2? Like, I mean, I might go through, like, for instance, contacting the community college and getting at its fume hood, and taking a Switch, Tegra chip, the T239, and using acetone and nitric acid to wipe away some of that stuff protecting it and everything. But I started to ask it some really basic and fundamental questions, because this is a world that I don't really know a whole lot about, and I'm obviously, you know, coming to realize just, how stupid I am, in regards to this. Like, maybe not stupid, but obviously ignorant. I'm confronting the reality of my own ignorance at this point, because there's a lot of things that I didn't know about, and looking at this, and what potential options we might have for such an advanced security system. I mean, this is really advanced stuff, and I want you to know, like, just how incredibly difficult it would be to attack the Nintendo Switch, and everything. And you're going to, well, like, first of all, you're gonna have to go through. You're gonna have to decap it, and then you're gonna have to map it, because you have a tripwire system that's in this and everything that will obviously go off, and if they go off, they trigger defensive behavior from the damn thing. They detect probing. Okay, so I asked it the question, tell me about the tripwire in the context of chip security, particularly with modern socks like the Tegra T239 used in the Nintendo Switch 2. Tripwires are protective mechanisms embedded into the silicon itself to detect tampering or unauthorized access. Here's a breakdown of what they are and how they work. Tripwires are physical or electrical features integrated into a chip's architecture that are designed to detect probing, decapping, or fault ejection attempts. They trigger defensive behavior such as wiping secure keys or disabling the chip. They monitor for unusual power draw, voltage fluctuation, or timing anomalies. They act as intrusion detection systems at the hardware level. I didn't necessarily know that this was even possible. There are types of them, which are metal mesh. A fine metal mesh sits just above critical regions, IG, key storage, and crypto cores. Any attempt to physically probe or mill the die, like with a focused ion beam, can break this mesh. Tamper detection logic will sense this and respond, blowing fuses and zeroing in memory. They, unlike a passive mesh, an active test carries a constantly monitored signal. It may send out a pattern, clocked or random, across this wire covering security zones. Any disruption, short, open circuit, capacitive change is interpreted as tampering by this thing. There are on-die sensors. Light sensors detect exposure to visible UV light from decapping. So at this point, you pretty much have to operate in perfect dark to get at this. You can't. Your clean room facility is also going to have no light as well. In this, you can't have any of it in it. It's going to have to be shielded from it entirely, so there's no UV light for them to pick up on. So this raises the cost, of operating in this environment. There's voltage checks, monitors that detect glitches, spikes, or dips that are common in fault injection. You've got temperature sensors that can detect abnormal heating or cooling, so you've got to keep the temperature constant in this thing. You can't have an unstable cooling system where, in the facility it's going to have to be strictly temperature controlled as well, for your lab to work on this. So you can't work on this in your home, so to speak, on attacking a system like this. You need a fucking clean room on several levels of, things are needed in your clean room facility. What happens when the tripwire is triggered? Depending on design, the chip might permanently blow e-fuses that destroy key material. The thing will enter a brick state. It'll power off instantly. It'll lock down the debug interfaces. JTAG, UART, etc. It'll send a signal to external systems that tampering occurred. Obviously there have to be ways to deal with this. In terms of security, you obviously would also probably want to have your facility, shielded in such a way where there was a Faraday cage
you would also want to be in a perfectly dark Faraday cage type scenario too, so that signals don't, they can't be sent to anybody that tampering is occurring, at all. They can't know. Why are they hard to bypass? Because trip wires are physically buried under multiple metal and preservation layers. They're sometimes connected to undocumented logic. They're designed to fail securely, meaning if they break, the chip dies or locks up. Built using randomized routing or obfuscation so attackers can't easily map or identify them. How do people try to work around them? With a focused ion beam editing with extreme precision to reroute or bypass tripwires without breaking them. Decapsulating under infrared or acid imaging to reverse engineer the layout before cutting. Fault injection with laser or EM pulses to try to skip over security checking logic. Decoy attack paths such as triggering an error on purpose to watch how the system handles it. These methods are expensive, dangerous to the silicon, and rarely you know, uh, rarely effective. Basically, they're rarely guaranteed. So you know the how you avoid triggering them. You work in total darkness or under red light, basically to avoid light triggered sensors. You keep the temperature constant within normal chip operating ranges, and you avoid strong magnetic fields, even from tweezers or motors. You also have to use precision power supply with a soft start. You ramp voltages slowly and smoothly. You log power consumption if sudden changes occur. A tripwire may be activating. Obviously, at that point, you need to be able to shut down immediately to prevent that from happening. Oh, you want to operate in ESID safe, wrist wraps, anti-static maps. You want to use proper grounding techniques when connecting probes. You use non-invasive imaging first. Before doing any cutting, you use X-ray or IR microscopy or SEM scan electron microscope. Identify potential sensor areas or unusual logic blocks. You also simulate before you touch. You extract and simulate firmware using emulators, e.g., QEMU. Look for anti-tamper routines in boot RAM or secure monitor code, and avoid running code that might check view states or unexpected I/O accesses. Never probe crypto engine buses directly. Instead, monitor power rails or bypass paths. Look for test pads or debug muxes left over from factory QA. These are signs you may have triggered a tripwire: sudden fuse burnout, loss of access to JTAG or UART or recovery mode, sudden current draw spikes or permanent current floor, EMMC or DRAM or scrambled or inaccessible. So, you know, uh, these are high risk, and these are the ways to potentially disarm or bypass tripwires. You might use a focused ion beam to reroute tripwire logic at the silicon layer, but this would require decapping, which can be done with acids. But again, you're probably going to be wanting to work in a red light environment, if you work at all, basically. And you inject the fault right before detection logic runs, with a glitch tripwire check. This is really hard to time perfectly. you know you might reverse secure logic, find and patch check routine and firmware, but the firmware is not going to be readable, basically. Then again, the truth of the matter is that because of the needs to update security on the Switch 1, I do believe that we do have access to the firmware, to see it. But anyways, you mask ROM extraction. You remove metal layers to read ROM visually. This was used in the iPhone A series and Secure Elements. So I really think that we're probably moving into focused ion beam territory and working with a lab, and somebody like the Decap Lab for IKD tapping services, which they'll happily work with you, although they're probably going to need quite a bit of information about what you're trying to achieve, and they need to understand, for instance, that I'm not, even if hypothetically what I'm doing might lead to the Switch, to being hacked eventually, that, you know, going through this process is really just providing, documentation to the scene that it might use to write the firmware. Like, I'm not the person. I like, if I did this, if I went through this process, I would not be the person that was ultimately responsible in any way for any form of copyright infringement or anything. What I would be doing is providing information to the people that might take that responsibility on themselves. It has nothing to do with me in that case, despite whatever the implications of this may be for somebody like me. I'm just interested in it because, learning all this stuff would enable me to, repair and, all that other stuff in almost any type of scenario. And this is just interesting from an inherent standpoint. The security on this thing. It's rather remarkable and awe-inspiring that they were able to do this and to go, this far. And it's really astonishing what you would have to do in order to to avoid triggering these systems. I mean, you don't what a consumer has access to just doesn't have that kind of precision on an ordinary level. You need, scientific power systems that, are able to provide completely precise, power situations to things, then so that there's no, unstableness, which means that you're, whatever you're putting things in, like your uninterruptible power supply is going to need to be engineered in such a way where it has the capacity to take in electricity from the wall and store it for a time period in case there's a fluctuation in the power grid and everything, so that it can smooth out that and make sure that the flow to your project is completely constant. And you're probably going to want a very large battery so that it can do this over a very long period of time. You're also, you're going to be wanting to work in a, when you do this, you're going to want a clean room facility, basically, that's dust filtered and everything, that none of that stuff can get into it, because when you delid the damn processor, you're basically rendering everything, more vulnerable to environmental contaminants, and so they all have to be filtered out, so nothing potentially touches it. And you can't operate in an environment where there's any light in the room unless it's red light. You need a infrared lighting as well in your facility, just so people can see what they're doing, but you're not triggering anything. And that's the only kind of light that you can have in the facility that does this kind of work. And that kind of lab is awe-inspiring and fascinating to realize that this is what you would have to go through. And I say this because when I looked into it and when I think about it and everything, the most I just think that Nintendo, has really done their homework on creating this. Now that I really know, and that I've got some more increased awareness about how this all operates, I think they've done a very good job, and I can't help but do my hats off to them, because I'm impressed at the amount of security that they've added to the system, the amount of learning they've done, and from prior mistakes. There may yet still be bugs in their code, especially in today's environment of hacking, because among other things, you live in an environment where if you work for a corporation, you're operating off deadlines and everything else, and this all but ensures that the programmers will not write the code even on the the wrong level in a perfectly secure fashion, just secure enough. So there may yet still be bugs, that end up being exploited, in this system. But from from all appearances, it's pretty hardened against security, against hardware exploits, which really, I mean, it yields an environment in which we're going to need clean room facilities to hack it. And while that might sound cost prohibitive, you need to hold up, you need to have a more sophisticated understanding of things. Access to clean room facilities is obviously being democratized because people in the academic settings, are obviously very interested in this kind of thing and are very interested in, having access to this. And, you know, um, like I said, and was going over, the deleting process can, basically just require a fume hood, nitric acid, and acetone to melt, to dissolve away the layers that are protecting it and everything. And but again, you need a fume hood to work with that stuff, and you might be able to rent or access a science lab at a community college to do something like this, and everything, and they will let you do it to a certain extent because it advances our scientific understanding of this sort of thing. It's an atmosphere of curiosity and research, you know, and like I said, the level that I'm operating on studying this stuff, I can't really be responsible for what other people do with what I'm studying at this point. If I yield useful information to them, you know, that's that's great and all, but you know what I'm trying to say is that I would not ultimately be responsible for the copyright infringement because you would need somebody else that had experience writing assembly, the portion of it that had to be written in assembly, and then the rest in C. Yourself and everything when it came to writing a mod chip out of this. But I do think everything that I've studied at this point, and looking at the attack surface that's potentially able to be done, I really don't know that there's any way to get at this system except to do focused ion beam editing. I really don't. And unfortunately, in order to even proceed down that rabbit hole, we're going to need to have a very, very precise map of things at very, very high resolution, so we can see the circuit layout and everything and do analysis to find out where these tripwires are to avoid them, and to see the wires leading into them so that we can potentially reroute around them, and disable the pathways to them, in a secure fashion. And this is mind-blowing shit, to say the least. I mean, my brain is blown at this point, seeing this and seeing the security upgrades that have happened. They really did their homework on this one. The chip that we're talking about, like, you can't. Why I feel this way? There's no, like, the secure portions of it are an internal, like, all right. How do I say this? Like, it's a sock. It's got multiple cores. Those cores are set up in such a way where the cores on the CPU or the sock or whatever you want to call it, they're all baked into it. The verification channel happens internally on one of the cores of the damn system, that verifies this logic. And there's nothing to solder onto, at this point when staging things. There's really nothing that you can put a probe at or anything that you can really do that without triggering security mechanisms on this internals. And so the only way that you're going to get at this is to find some way to interfere with the internal logic on the sock itself, which is technically feasible, but it's incredibly difficult, to say the least. You're going to have to do like nanoscale surgery on it, which means you're going to need a clean room facility and a lab, and you're going to need to be able to talk the lab into it. And this would enable you to reroute the logic on the chip so that you were able to bypass all the security mechanisms, and they would probably work with you simply because, like I said, you know, the benefits that we gain as a civilization from understanding this sort of thing are more important than the intellectual property it may enable, you know, them to steal. Do you get what I'm saying? It would train a whole new group of people on a, you know, something that they would find interesting, basically.